All right, let's go ahead and get started. So today, lecture 20, 2/3 of the way through the course, we're going to be talking about ensemble methods. So for pretty much every lecture for the last 15 lectures or so, we've introduced new classification methods. And in today's lecture, we're not going to be introducing a new classifier, but rather we're going to be introducing a way of combining existing classifiers together in order to get a better classifier than any single classifier working on its own. So these methods are called ensemble methods. I think they're really cool, and hopefully you guys agree. So a couple of brief announcements. The discussion sections for tomorrow afternoon, tomorrow evening, is going to be a tutorial on PyTorch. So PyTorch is Meta's Python library for deep learning. It's open source, pretty popular. PyTorch is really kind of the gold standard for sort of research work in deep learning nowadays. So most people who I know like PyTorch over the other packages, which is why I chose to do PyTorch for this tutorial. I recommend you guys install this before heading to the discussion section. It can take, maybe 5-10 minutes to get installed on your system. So you can check out the link here on the slide to go ahead and install that before attending the discussion section. The main reason that we're doing a tutorial on PyTorch, rather than just saying, okay, use scikit-learn for your deep neural networks, is that really the neural network implementation in sklearn is a little bit outmoded. So really, if you want to do anything with neural networks, you'll be using a more modern library like PyTorch. So for example, if you're interested in working with CNNs that we introduced a few weeks ago, these convolutional neural networks, you'll probably want to use something like PyTorch over scikit-learn. So it's good to know how to use this, just be familiar with the basics. And if you're interested in working with it on the projects, say with some of the image data sets, this will be a handy way to get started there. So definitely worth attending. I got a nice tutorial lined up. Okay. So today we're going to start out with just a quick wrap-up on decision trees. We'll actually also analyze their time-space complexities. After that, we'll start our discussion on combining classifiers. So these are the ensemble methods that I briefly mentioned. And at the very end, we'll introduce these things called random forests. Okay, so you're probably sick of seeing this picture by now, but really this is sort of the canonical image you should have in your mind whenever you're thinking about a decision tree. We've got some data, and our tree is kind of partitioning the space into disjoint regions, where in each of these disjoint regions, I'm kind of computing a class probability vector corresponding to that region. So this tree implements this kind of split on the left-hand side here. We've seen this algorithm build tree a few times. I assume most of you guys haven't started working on the homework yet, but you'll be implementing this. And again, the idea is that we're going to recursively build our tree by creating a new node, computing those class probability vectors at the current node. If the node meets some condition for being a leaf, we'll stop and just consider that node to be a leaf node. Otherwise, we find the best possible split our data, and then recursively continue. So I've described this find best split step a couple of times in words and in text, but I thought it would be a good idea to just introduce some pseudocode here, especially because you guys are going to be implementing this in homework 4. So given some labeled data set D consisting of feature vectors X and labels Y, at the current node we're considering, we'd like to find the best split somehow of this data. So for example, think of this at the root node of our tree, but it's the exact same procedure at any other level. What we need to do to find the best split is to iterate over all of the features. So we've got D features here, so we're doing a for loop over each possible feature. Our first step is going to be to sort the values for that feature. And the reason we need to sort them is because we need to know where our thresholds are. Again, our thresholds are placed between consecutive data points. So of course, we need to sort them in order to find those thresholds. Then for every possible threshold, there's n-1 of these because we have n data points, so we only consider thresholds between our data points. We'll compute the class probabilities and the Gini scores, as we've seen how to do in the examples. And then whichever of these thresholds has the minimum Gini score, we'll set that to be sort of the best threshold for this particular feature. Then at the end of the day, we find the threshold and the feature with the minimum Gini index. So again, we loop over all features and all thresholds. And just a reminder of how we pick these threshold values that we're considering. Well, any threshold that's between sort of consecutive data points is going to be an equivalent threshold for the context of computing a Gini score. So in practice, we even pick just sort of the midpoint between our features after we've sorted them, of course. Okay, so let's think about the time complexity of this find best split step. Really, this is the expensive part of our algorithm, so we can just sort of analyze this and pretend everything else is cheap enough. So we're going to assume here that the number of data points we have is n, and the number of features we have is d. And both of these are much, much larger than the number of classes we're considering in our data set. So anything on the order of capital K here, I'm just going to essentially disregard. So our first step, our for loop over the total number of features we have, is of course an O of D operation, linear in the number of features we've got. Our sorting algorithm, let's say we use an n log n sorting algorithm. So that's just the sorting step. Then we have O of n thresholds to consider. So this is an O of n operation within our outer for loop. And these two steps are cheap enough that I'm just going to consider them to be O of 1. Okay, at the end of the day, I need to find the best threshold, which means finding the one that had the minimum feature value. And I can do this just linearly in n by just iterating over all the Gini scores that I've computed. So this is an O of n operation. And at the end of the day, I need to find the best threshold over all of my possible features, and this is again going to be an O of D operation. So overall, combining each of these steps, the time complexity of computing the best split at a single node, just putting everything together from the previous slide, is going to be D times n log n. So it's linear in the number of features we have, O of D, and it's n log n in the number of data points we have. This is obviously not ideal, we would like something that's maybe linear in n, but n log n isn't too bad. So this is again just for computing a single split at a single node. But if we say have a tree of depth L, well, we of course need to do this say L times. So in the worst case, we'll have something like O of L times D n log n. Oftentimes, however, you can kind of do tricks to save computation. So a lot of the steps you do at the root node, say computing thresholds and computing probability vectors and things like this, kind of sort of be stored after our computations at the root node. And so in practice, we can do some tricks here to reduce the complexity. So oftentimes, we just say that a decision tree has complexity d times n log n. Okay, so this is training a decision tree, kind of expensive. But at prediction time, it's actually significantly cheaper. So let's say we just have binary features and a max depth in our tree of L. Well, to make a prediction on a single data point, it's easy enough. We just need to traverse our tree and then essentially return those probabilities in the leaf nodes. So the time complexity for making a single prediction is just essentially on the order of the depth of the tree, which is O of L in the worst case. The space complexity is a little bit more expensive. Essentially, we need to store the information contained at each node in our tree, so it's going to be on the order of the number of nodes. And so in the worst case, if we've got a fully filled out binary tree here, the number of nodes is going to be the number of leaves plus the number of internal nodes. And it's going to be in the order of, say, 2 to the L plus 1, just counting up all the nodes in a binary tree with L layers in it. So overall, again, prediction with these methods is pretty cheap. It's only linear in the depth of your tree. It doesn't scale poorly with the dimensionality of your data or the number of data points. But the space complexity can be kind of high if you've got really a massive tree. Okay, and just to summarize, just to have everything sort of in your brains fresh and ready to go, decision tree classifiers are very, very flexible models. We can grow them to be very deep and learn very complex decision boundaries. But of course, all of these decision boundaries are going to be parallel to the axes just because we split on a single feature at a time. Each internal node in our tree represents a split on a particular variable, and at the leaves, we return, again, this vector of class probabilities. We've seen a couple of examples of how you learn decision trees. It's this kind of local, greedy scoring algorithm where we use this Gini index to find the best split. And the time complexity scales with the number of nodes in your tree, the depth of your tree, the number of features you have, and the number of data points you have. Okay, so any questions on decision trees before we start putting them into ensembles? Yeah. Yeah, so just to reiterate, the question is, well, we've seen a ton of models at this point. Which one should I use for my problem? And the answer is, try them all on your data set and see whatever does best on the validation data. So really, it's a big model selection problem. you can almost think of what model you're using as like a hyper parameter, right? It's another choice you make before you fit your data. So you just got to try it on your data and see what works best. But that is a good segue into the second part here, which is, well, what if I don't want to pick a model to use? What if I want to use all of my models? So rather than choosing a single model, what I might try to do instead is somehow fit a bunch of models and then combine their predictions and get a single model at the end of the day that I can use for my task. And so we're going to see how to do that in today's lecture. So first, let's introduce a little bit of notation here. We're going to assume in today's lecture we're doing binary classification, so just two classes, y equals 0 or y equals 1. But all the methods that I'm going to introduce here, it's straightforward enough to make this work for multi-class problems. But just to keep the notation simple, we're going to do binary classification here. I'm going to use f of x throughout to represent some pre-trained binary classifier. So f of x is the output of some model that I went ahead and fit to data, given some input features x. So f of x is some prediction model. These models, of course, have some associated parameter values. It might be like the weights in a logistic model. It might be the tree structure in a decision tree. But I'm just going to drop this conditioning on theta just to keep the notation from being too ugly. And again, in this section, we're always going to interpret the outputs of our model as some probability. So we interpret f of x as the probability that y equals 1 given our data point x. So it's what's my model's confidence that the label is 1. And we're, of course, parameterizing probabilities here, so this number is going to be between 0 and 1 always. But f of x could be any of the models that we've seen so far in the class, like a logistic model, a neural network, a decision tree, could be k and n even. We didn't really discuss in the k and n portion of the lectures, how you can turn k and n into a probabilistic model. But this is pretty straightforward. Rather than just returning the majority vote of the k nearest neighbors, you can just return the fraction that were belonging to class 1. So all these models can return probabilities as their predictions. Next up, we're going to use y with a hat on top of it to denote the class label predicted by a classifier given features x. So in the previous slide, we used f to denote the predicted probabilities. Now we use y hat to denote the predicted labels. So for binary classification, the way you can kind of go between these two representations is if your model predicts a probability of larger than 0.5, well, it thinks it's more likely that y is 1 than y is 0, so I'm going to predict y hat equals 1 for that input. So I can turn probabilities into sort of hard labels. And conversely, if my probability is smaller than 0.5, I'll predict a label y hat 0. So you can kind of simultaneously think about your classifiers as, again, predicting probabilities and predicting hard labels if we need to sort of make a decision at the end of the day. More generally, if you have more than 2 classes, so if you're working with, say, 3 or 4 or however many classes you've got in your problem, to turn those probabilities into a predicted label, you just take the argmax of the predicted probabilities. So whichever probability was highest. Okay, so now that we set the stage with some notation, we can introduce the idea behind ensembling methods. So there's a long line of sort of research in cognitive science and psychology regarding the wisdom of crowds, it's called. And the basic idea here is that by combining the predictions from multiple people, you can do better on some kind of predictive task than any single individual human would do. So the classical example here is called Galton's ox, way back from 1906, where at some county fair, there was a game going on where people would come up, try and guess the weight of an ox, and try and win a prize. So got some graffiti back here with cows. I don't know if you guys can see it. I didn't draw this, but it's topical for this example, I guess. Anyway, I guess this is what they did for fun back in 1906 at county fairs. But it turns out what the scientist Galton discovered is that if you take the average of the predictions from all of the crowd, so you just average up the guessed weights, it turns out that this is much more accurate than any individual person's predictions. And in fact, the average of, I think it was 800 participants, gets within 1 pound of the true weight of some 2-ton ox. So this is really interesting because, individual people maybe don't do so good on this, but get a bunch of people in a room together and you can do pretty good at hard problems. So as this example demonstrates, maybe we can take this kind of intuition and now apply it to machine learning. So rather than combining predictions from humans, could we somehow combine the predictions from various classifiers? The intuition you should have in mind is that if your classifiers kind of have different expertise, if they're good at different subsets of your data, well, then it's worthwhile to combine them on your problem because they might be making different errors now. And so for some terminology, ensemble methods, which is what we're talking about today, are any kind of techniques or algorithms that are used to combine different classifiers. And when I say an ensemble, I mean just a combined classifier. I think these methods are really cool, and in fact, we wrote a paper on this a few years ago, where rather than combining human predictions or combining model predictions, we actually combine predictions from a machine learning model with human experts. So you can actually use these methods to sort of combine people's decisions with decisions from a model. This is really useful in like a medical diagnostic task, right? You have an algorithm predicting whether or not a patient has a disease. You have a doctor predicting whether or not a patient has a disease. And actually we showed that sort of the combination of these two is better than either working alone. So really these ensemble methods are great for getting good performance from your models. Okay, more notation. Let's say we've got capital M pre-trained classifiers. So what I mean is I have some data set and I went out and trained M different models. The class probabilities, i.e. the predicted sort of outcomes from each of these classifiers, I'll denote with a subscript. So F sub 1 is my probabilistic prediction from my first classifier. F sub little m is my probabilistic prediction from my mth classifier, so on and so forth. And of course, I can turn these into sort of hard or predicted labels from each classifier by just taking sort of that threshold from the previous slide. And again, y hats indicate these hard predictions. And I'd like to emphasize here that the M classifiers that we've trained don't need to be the same types of classifiers. So maybe we have 8 different classifiers trained for a problem. Maybe 3 of them are neural networks, 4 are decision trees, and 1 is a logistic classifier. So really, this is a very general setup. We've just got M classification models. Okay, does anyone have a guess on how I could combine my models? Maybe what's the simplest thing I could do? Yeah, I see one hand, but maybe someone who hasn't answered a question before. Yeah. Yeah, you're getting ahead of me, but we'll eventually see that. Any other guesses on how I could combine these? Even simpler than averaging probabilities. Yeah, in the back. Majority, yeah. So the simplest thing I can do is just take a vote, basically. Maybe my models are very democratic and everyone gets an equal vote. So I have M pre-trained models, all trained on the same data set D. For a new data point, X, coming in at testing time, what I can do is I can compute sort of these hard predicted labels from each classifier. So I take X, stick it into every one of my models, and get M predicted labels. And now for my combined prediction, what I can do is just take the majority vote of these classifiers. So whatever label was predicted most frequently is going to be my output. In practice, it's good to have M be an odd number if you have a binary classification, so we don't have to worry about breaking ties here. So let's see an example of how this works. Here I've got 3 classifiers on a binary classification problem, and each one gets roughly the same error rate. So each one is doing pretty much the same as all the others, but they have different decision regions. So blue shading and red shading, of course, indicates what these models are predicting. If I take the majority vote coming from these 3 classifiers, I get a new classifier that now has a significantly more complex decision region. So essentially what's going on is maybe at this point, well, all 3 of my classifiers agree that this point should be classified as blue. It's blue here, and blue here. In this region, 2 out of my 3 classifiers agree that this should be predicted as blue. This guy and this guy think it should be blue, but this guy thinks it should be red. So we predict blue down here. In this region, 2 out of my 3 classifiers think this point should be predicted as red. So overall, voting is a very simple way of combining classifiers. And what you can see here in this example is my error is now 0. By just taking a vote of my 3 classifiers, I got that error rate to be 0%. Okay, so other than voting, I was planning to ask, are there any better ways than just simple voting? And someone said we can take the average of the predicted probabilities. So rather than taking hard predictions from my models and taking a majority vote, what I can do is just take those probabilities, the soft predictions, and now average them up. So this expression here, of course, is just a sum over all of the predicted probabilities from my model, and I divide by capital M to take an average. Okay, because we're taking an average here of numbers between 0 and 1, the predicted probabilities, the output here, this f of x, will again be a predicted probability, some number between 0 and 1. So what this means is we can kind of interpret f of x, the average probability, again as a probability of the label being y equals 1, given some data point x. And of course we can threshold this, f of x with no subscript, at say 0.5 to turn it into a hard label now. Okay, so there's a pretty serious problem with averaging these probabilities. So does anyone have a guess of what can go wrong if I just average a bunch of classifiers together? Yeah, in the middle. So in this case, we're just trying to predict, say, y equals 0, y equals 1, so yeah, maybe not. Yeah, another guess. What can go wrong here? Yeah. So what do you mean by outliers? Yeah, okay. So the suggestion was there might be some outliers in these predicted probabilities, some that are too high or too low. That's exactly what goes wrong. So imagine you have 10 classifiers. 8 out of 10 of your classifiers are great, doing what they should be doing. Maybe 2 of your classifiers are awful, just making random guesses. Well, if we just take this sort of very simple averaging method or a majority vote, well, you don't really want to trust those bad classifiers, right? You're kind of incorporating bad predictions into your final ensemble. So in some sense, we would like to sort of look at our models, see which ones are doing good, which ones are doing bad, and use that information to decide how to combine the classifiers. So what we can do instead, rather than just a simple average of the probabilities, is maybe take a weighted average of these probabilities. So here I introduce now a weighting term, W sub m, where these weights, W sub m, are numbers between 0 and 1, and we're going to assume that they sum up to 1. So in other words, I'm taking a linear combination of my predicted probabilities. By this choice of the weights, we can see that because they are constrained to be non-negative and sum to 1, the weighted sum here, the output, is again going to just be a predicted probability between 0 and 1. So of course we can again interpret this weighted ensemble as a predicted probability. And unweighted averaging, of course, is just a special case of this where all of the weights are equal to just 1 over capital M. So really weighted averaging is a more general way of doing ensembling. But we've got a pretty big question here. How do we learn these weights? We don't want to pick them by hand, of course. Maybe you've got 1,000 models in your ensemble. How could you possibly choose these weights? So what we're going to do is something called stacking. The idea behind stacking is we're going to take our data, and we're going to again split it into a training set and a validation set. On our training set, we're going to fit our M models. So we fit every model on this training data set. And then what we're going to do is we're going to take our M models and learn the corresponding weights of these models using the validation data. In other words, we're going to somehow fit a logistic model using, say, cross-entropy loss on top of the predictions coming from our original models. So we'll see an example of this on the next slide, but the idea is we'll use validation data to learn these weights. Okay, question for you guys. Why should I not use my training data to determine the weights of my models? Okay. Let's see. Got 2 hands, but in the spirit of new people, yeah, in the middle, green sweatshirt. Yeah, exactly. So the suggestion was the model might just overfit the training data, and that's exactly right. So you could have models that get 100% accuracy on your training data, but don't generalize at all to unseen data. Well, if you fit your weights using that training data, you're going to upweight those overfitting models. So we need to assess the model's performance on some held out data, some validation data, in order to really assess how well these models are doing, and that performance is what we care about when we would sort of determine the relative weighting of the votes here. Okay, let's see an example of what this stacking procedure looks like. So I've got some validation data consisting of feature vectors and their corresponding labels. And again, this is data that these original models are not trained on. And what I do is I take this validation data, these validation feature vectors, and I pass them through every one of my M pre-trained models. So now I get a prediction for every single one of my classifiers on every single one of my validation data points. This is a typo. This should be F sub capital M in the final column. But now we can kind of forget about the fact that we had validation at all in the first place. We've just got a big data set here, right? Where each of these columns, the first M columns, is some inputs, right? And we're trying to predict some labels Y from those inputs. So what we can do is, again, just treat this like a new classification problem, where we essentially take the predicted probabilities coming from our new models and feed them into some second level or sort of downstream classifier. So in other words, I could say fit a logistic regression model on top of this new data set on the right-hand side. And in this way, I'm going to be able to learn weights associated with each of my M classifiers. And really, this is all there is to stacking. I'll take questions in one sec. So I'd like to point out here that stacking or ensembling is really quite a popular choice and works very well in practice. So for example, there is this Netflix prize challenge held between 2006 and 2009. Believe it or not, this is indeed what the Netflix website looked like at one point, back when they actually mailed out DVDs to people. But the goal here was to predict user ratings of movies that the user had not seen before, just based on how they rate other movies in the database. And the winning entry here used a stacking method, i.e. ensembles, and was actually able to beat Netflix's previous algorithm by something like 10% in accuracy, which is a huge boost just by applying stacking. And so they won $1 million for this at the end of the day, so just goes to show, stack your models if you want good performance. Okay, so to sort of summarize ensemble and stacking methods, if we've seen them so far, is that you've somehow got M different classifiers trained on the same data set, and we combine them in various ways. Say voting, very simple. Averaging, also very simple, but again, can't really take into account model performance. And really the most popular one here, best performing one, is going to be something like stacking, where you learn weights associated with each classifier. Okay, any questions? There's one back here. Yeah, exactly. So to reiterate the question, why do we fit our sort of stacking model only on the model predictions? Why don't we put the feature vectors also in this new data set we're creating? You can absolutely do that. So oftentimes this will get you slightly better performance, but at the cost of now you have a much more difficult prediction problem. So here, for example, you could fit a very simple logistic model on, say, maybe you have 1,000 classifiers, so you can learn 1,000 weights. But if you have a very high dimensional prediction problem at the first place, like maybe you're classifying 1,000 by 1,000 images, so it's very high dimensional, you're going to need a much more complex model to stack them. So it's a trade-off between very complex model and maybe small but significant gains in performance. But yeah, you can absolutely do that. Okay, other questions on stacking? Okay, cool. So now we're going to introduce a sort of set of techniques called bagging and random forests. And these are particular examples of ensembling methods that are quite popular out in the sort of real world. Okay, so we've briefly talked about this idea of sort of classifier variance before. But really, again, just to drive home this point, when you're building a classifier, there's variance in the models that you'll learn from data. In the sense that if I have a data set coming from some problem, and if I have another data set coming from the same problem, but maybe is slightly different, maybe I have a subset of my original data, by the variance of a classifier, I mean how much does the model I learn change if I make sort of small changes in my original data set. So for example, if I have some data set D, and I just split this data set in half into equal size subsets, a model that has high variance is going to learn very different models on these two splits of my data. Okay, let's see an example of what this looks like. So here I'm looking at my Penguin data set, where I train on a random subset of this data, just 10% of it. And I get some small decision tree here. If I take a different random 10% of my data and train a decision tree on top of that, I get a very different looking tree. So originally my first root node in the first tree is the first feature, x0. And down here I get a new root node, which is x sub 2. So again, the idea is I have sort of data from the same problem, but I'm somehow learning very different models just because of sort of the randomness inherent in my data. And so we say something like a decision tree has high variance because the actual trees you get are very sensitive to small changes in your data set. So decision trees have very high variance, but in contrast, sort of linear models like logistic regression or nearest centroids tend to have very low variance. Even if I look at slightly different data sets, well, the best linear decision boundary isn't going to change all that much. So linear models are good examples of low variance models. As we saw before, high variance contributes to testing error. Again, testing error is kind of a sum of bias and variance. So if we can, we would really like to somehow reduce our model variance. And one way to do this is to somehow average over different models. So just like we've been doing in ensembling. So again, ensembling is really a way of reducing variance in models. Okay, so in the ensembling setup we've seen so far, we've just assumed that we're given m different models. But of course, if you fit a decision tree to a data set, well, if you fit m decision trees to the same data set, you'll get the exact same model m times. And of course, this isn't very useful to average over. So we need some kind of way of building new decision trees for the exact same data set that, again, capture the data but look a little bit different from one another. So the general idea here is we're given some training data set with n data points. And we're going to somehow randomly generate capital M random subsets of this data. For each of these m subsets, we're then going to fit a tree to that data, and then combine these trees through something like voting or averaging or any of the methods we've seen so far. So again, the idea is we want to have m different trees on our original data. And the only question here that we need to figure out is, how do we actually generate these m random subsets? We already know how to fit trees, we already know how to combine them. We're going to do this using a procedure called bootstrapping. So we saw bootstrapping before in the context of model selection, but now we're going to use it for something slightly different. And the way bootstrapping works is we've got a data set capital D with n training points. And to construct a bootstrap sample, which I'll call D sub m, it's going to be a new subset of my data having the same size as the original training data set. And we generate it as follows. We're going to initialize D sub m as an empty set. And then we're just going to iterate n times. And each iteration, we're going to randomly pick a pair from the training data, so just a random row in my data matrix, and add this pair to this bootstrap sample D sub m. Or in other words, we're creating a new data set having the same size as my original, except I'm sampling with replacement. So what happens is the same data set can now appear multiple times in a sort of bootstrap sample. So let's look at an example of this. Say we've got a really tiny data set D here. In my first bootstrap sample, I just select 5 random rows from my original data set with replacement. So this first row now appears twice. This row also appears twice. I do this again, but get a different random sampling of my original data. So I create a new data set that looks like my original data, but it's slightly different. Do this again, get a third data set, and get a fourth data set here. So we're kind of adding noise to our data is the idea to get similar data sets, but not exactly the same. Okay, for a brief aside here, how do we actually generate these sort of random samples from my data set? And again, we need to select random indexes, right, when we're selecting random rows. And the way we're going to do this is just using random number generators, of course, but hopefully you guys have seen something like this before, but it's good to see the internals of how this actually works. So most programming languages, to get a random number, you work with a pseudo-random number generator that, given some seed, produces just a really long string of random integers. They're not exactly random, but random enough for our purposes. If we divide this really long string of integers by the maximum value it can take, you'll get a random number between 0 and 1 that approximately is uniformly distributed. So a random number between 0 and 1 is what we get. And this is really the basic random function that you work with in most languages. And we can use this random function to randomly select rows from our training data as follows. So let's say we're selecting from a data set with 5 rows in it. When I randomly generate a number in this way, I get some random number between 0 and 1. And let's say when I get that random number, it falls somewhere in this interval. Well, because it falls in my second interval, I'll select the second row for my data set. If I get another random number between 0 and 1, it falls in this sort of fourth interval here, so I'll select the fourth row in my data set. Select another random number, it falls in this range again, so I'll select the second row once again. So this is just some details on how random sampling is actually sort of implemented in practice. Okay, so now that we've seen how to create bootstrap samples of our data, let's see how to put these together into a machine learning algorithm. And this is called bagging, which is short for bootstrap aggregation. This was introduced way back in 1994, so in the context of machine learning, this is sort of an ancient method, but really still gets used today. And the training procedure here is we're going to generate capital M bootstrap samples of our data, so we make a bunch of new data sets. We fit a decision tree to each of these data sets, resulting in capital M different decision trees. And again, we just use the sort of standard learning algorithm we've already seen. And then we just combine these models using ensembling. So to make a prediction with, this bagging method, for some new data point x, we make a prediction with each of these M trees, and somehow combine these predictions, say taking an average. There's some really nice theory out there that tells us that this has the effect of reducing the variance of our trees compared to using just a single tree. Oftentimes, these methods, when you use them with decision trees, are called random forests. The idea being, you have a bunch of trees now that you're combining, so you get a forest out of it. You, of course, can use the same procedure with methods other than decision trees, but really that's the most popular sort of model that gets used here. Okay, so let's see an example of what's going on here, what this looks like. So here in the top right, I've got a single decision tree fit on my full data set. You can see I've got some pretty complex decision boundaries here, probably overfitting. If I sample one subset of my data and fit a decision tree to it, well, I get another decision tree that looks kind of similar to the first one, but slightly different. So this is what I mean by variance, that if I fit a model to very similar data sets, I get slightly different looking trees. Okay, if I look at another sample, another bootstrap, I'll get another decision tree, yet another one, okay, so on and so forth. So in total, I can fit, say, 5 different decision trees on different bootstraps of my data. And again, this bootstrapping set is absolutely essential, because otherwise we would just get the same tree over and over again, and it wouldn't be useful to average over. And then at the end of the day, we can just take these trees and ensemble them using the methods we've seen before. In effect, this helps us sort of reduce memorization from our trees. Because not every decision tree is going to see every data point, there's going to be some left out just by our bootstrapping process. It essentially helps fight this memorization, helps fight overfitting. In essence, by averaging over many trees, it kind of reduces the overall complexity of any particular tree. And usually this results in better generalization performance. So the average of my 5 trees looks something like this, which, as you can see, kind of reduces these sort of overfitting regions that you might have originally seen up here, and hopefully is a bit better of a model. I can average over more than just 5 trees here, so I control how many bootstrap samples I have. If I use 25 trees, I get an even better fit, and if I use 100 trees, I get something that looks pretty great. Okay, we've seen this graph probably 100 times by now, but really you should keep this in mind throughout pretty much everything you do in machine learning, where the idea is, again, we want to have a model right here in the middle with low bias and low variance. And by doing this bootstrap aggregation, we get models that have low bias because they're all based on trees, very flexible, but also we somehow reduced the variance by averaging over many bootstraps. So bootstrapping is trying to get us right in this Goldilocks zone here. One limitation of these bootstrapping methods is that if you apply bagging to a decision tree, if you have a very large data set, oftentimes you're just going to learn roughly the same tree at the end of the day. Even if we resample our data, it doesn't really matter. We've got enough data that each tree looks pretty much the same. And so one way to sort of introduce extra variation in our trees, again, we want this variation, we want sort of diverse models, is that each step, we only allow a random subset of the features to be selected. So rather than looking at every single feature in my data set when I'm creating my decision trees, I only look at some subset of these features. And again, here we're introducing more diversity into the trees that we learn. So random forests are essentially doing this. So in a little bit more detail, what's going on is I create my M bootstrap samples as I had done before, so my random data sets. And I fit a decision tree to each of these M bootstrap samples. But when I'm searching for the split at every node in my decision tree that I'm fitting, I only search over a small subset of the original features that were available. So there's this additional randomization step for these things that are called random forests that goes on top of this bootstrapping method. And at the end of the day, we get M trees, just as we had before, and we can combine them in the same prediction procedure that we've seen several times at this point. Okay, so any questions on random forests, bootstrap aggregation, any of this stuff? Yeah. So this is all done on the training data. So you take your training data set and split that into several bootstrap resamples. And then if you have hyperparameters, which we'll see in a second, then you can use a validation set to select those. You definitely do not want to be fitting on your validation data. So these models have hyperparameters associated with them, like how many trees do I fit here, right? What's the right number for capital M? And you don't want to be selecting that on your training data. You're going to overfit. Okay, other questions on random forests? Yeah. Exactly, yeah. So the only difference here between bagging is that we only look at a small subset of the features when we're constructing a particular tree. And again, the idea is we want to encourage our trees to be more diverse, and this is one way of doing that. Okay, so let's talk about hyperparameters for these models. So the main hyperparameter introduced in terms of a random forest are the number of trees that we're going to be selecting. So how many models are we averaging over? So the default value for this in something like scikit-learn is 100. So we're fitting 100 different models and averaging over those. We also need to select the number of features R that are randomly selected when we're constructing any node in a random forest. Sort of default here is it's the square root of the number of original features in your data set. I don't think there's a great reason this is chosen. I think it's just a heuristic that tends to work. Then, of course, we also have all the usual hyperparameters associated with decision trees, say the maximum depth allowed for each tree. Also, of course, consider other stopping criteria here, like minimum samples in a leaf node, so on and so forth. Okay, in scikit-learn, they've got this implemented for you. You can use it just like any other model. So this is a random forest classifier. And again, these important hyperparameters are the number of estimators, i.e. the number of trees in my random forest, the maximum depth allowed per tree, and you also can look at the minimum samples required to, say, split at a node. So again, there's a bunch of parameters here that need to be varied in order to get good performance. Let's look at some examples of actually fitting random forests now to some synthetic data sets. So on the x-axis here, I've got maximum allowed tree depth, and on the y-axis, I've got error rate. And for my red curve, I'm plotting the error rate on the testing data of just a single decision tree. And what you can see is this kind of classical overfitting shape, where model performance increases up to a point, but then when we make our tree too deep, it starts to increase. In contrast, a random forest plotted in blue, so an ensemble of 100 different decision trees, gets a significantly lower error rate pretty much everywhere. And also, interestingly, we don't see as much overfitting, right? This blue curve, the error rate doesn't really increase as much as this red curve is once we hit a certain maximum depth. Here, what I'm doing now is the same thing in the previous slide, but now increasing the number of trees in my random forest from just 100 trees up to 1,000 trees. And sort of what we can see from this is that effect of reducing overfitting is even more prominent here. So I can make the maximum depth in each of my individual trees pretty large. 8 is a pretty deep tree, but my random forest is still not overfitting the data. So this just goes to show that ensembling is a really great way of fighting overfitting and helping your models generalize to unseen data. In practice, usually you don't want to fit a random forest with 1,000 trees in it. It's going to be pretty large. So typically people look on something like the order of 100 trees in a random forest. Okay, same slide again, but if I reduce the number of trees down to 20, well, this is probably what you should expect to see, that our random forest starts to decrease in performance if we don't have enough sort of trees in that forest. Okay, so let's summarize random forests. Really, the strengths of using a random forest over a single decision tree is that you often get significantly better accuracy with a random forest as compared to just a single tree. The idea here is this is coming from a reduction in variance in the model. These models can produce very flexible decision boundaries. They're also scale invariant, just like decision trees, so we don't need to pre-process our data. We don't need to scale it. Again, we've seen that these models are less likely to overfit compared to other models. And really in the real world, in practice, these things are very widely used. So random forests are sort of the wrench in a practitioner's toolbox. Everyone reaches for these first. These are especially good for tabular data sets, say like medical diagnostic tasks, anything where your data is just kind of rows in some Excel table. Of course, these are not perfect models. They have some weaknesses associated with them. The first one is that they're a bit hard to interpret or understand. So we like decision trees because we can kind of look at the nodes and figure out what it's doing. But if you've got a forest of 1,000 decision trees, well, good luck figuring out what that thing is doing. So they're very hard to interpret. Your decision boundaries, because we're ensembling a bunch of decision trees, are still going to be axis parallel, so we kind of inherit that limitation from a decision tree. And another weakness here is that it doesn't really do feature extraction. It doesn't produce any kind of hidden representation. So unlike a neural network, our decision trees are still operating on the original data. They can't sort of extract features like we saw that a neural network can. And for this reason, if you have kind of natural data, sort of perceptual data like images, speech, or text data, random forests aren't going to do great. They just can't extract these features that we need in the way that a neural network can. Okay, maybe let's just wrap up and then I'll take questions afterwards. So today we finished our discussion on decision trees. We saw that their training complexity is linear in the number of data points and n log n linear in the number of features and n log n in the number of data points, so kind of expensive to train these. And at prediction time, they're cheap to query, so it's just on the order of the depth of the tree, but might be expensive to store if you have a lot of nodes. We saw how to do ensembling, where we can combine many classifiers together through, say, voting or averaging. And then we introduced weighted averaging, i.e. stacking, in order to kind of account for model performance in these ensembles. And then lastly, we introduced bagging and random forests, which are particular examples of ensembling methods, where the idea is we're going to create bootstraps of our data via randomly sampling subsets with replacement, fit a bunch of decision trees, and combine them. And again, the key idea here is you want different models in an ensemble. You need diversity in your predictions. And with that, we can end for the day. Thanks, everyone.